We will now shift to Daniel Gomez from University of British Columbia. Let me know if you have any trouble. Excellent, and I will let you take it away, Daniel.
All right, first of all, thanks for the invitation. I look forward to all the talks today, actually. So this is in collaboration with my PhD advisor, Yung-Cheng Wei at UBC, and I'll be talking about spike patterns in the Gierer-Meinhardt model, except this time we're going to consider the effects of boundary conditions. Very, very brief outline of what I'll talk about. I'll start by giving some background and motivation for looking at the specific problem, and then we'll jump right in and actually talk about this Gierer-Meinhardt model. So before I even start, I think it's good to point out that these two-component reaction diffusion models that we typically study, they're model systems, and so they're useful as a way of studying how specific mechanisms can lead to pattern formation. In the context specifically of reaction diffusion models, we're typically interested in what's the interaction between diffusivities, so like diffusion, and different types of reactions that can occur between species. And one way that this is often done is by studying Turing instabilities or diffusion-driven instabilities, by which a spatially homogeneous steady state of these reaction diffusion systems will suddenly turn into a spatially patterned state. And there are a lot of different aspects for how people have been studying this, and there are some issues with Turing instabilities, and people have been trying to address them by introducing different types of mechanisms. So again, going back to the idea of a model system, we can incrementally add more complexity to it and study the effects of adding that complexity. And the aspect that I'm going to be talking about today is actually what is the role of boundary conditions on such problems. So like I said, for Turing instabilities, you're always interested in how a spatially homogeneous steady state suddenly undergoes spatially varying perturbation or bifurcation. And oftentimes what one assumes is that you have homogeneous Neumann boundary conditions in this problem. However, depending on your choice of boundary conditions, you can find that there's actually quite substantial differences in the types of patterns that result. And this goes back to work by Dillon and others in early 1990s. More recently, one direction of kind of expanding the reaction diffusion and Turing instability mechanism has been to consider these things called bulk membrane coupled problems, in which problems inside of a domain are coupled to other problems on the boundary. And obviously the bulk problem has to interact in some way with what's going on in the boundary, and this has highlighted that we really need to understand what the boundary conditions are actually doing. So in order to start exploring this, we're going to talk about the singularly perturbed Gierer-Meinhardt model, similar to what Chunyi was discussing earlier. And we're going to look at what are the effects of introducing inhomogeneities into the boundary conditions on strongly localized solutions. So Chunyi already gave us a really good overview of how one constructs strongly localized solutions. I'll add just a few comments and say there is a wide class of singularly perturbed reaction diffusion equations where if your kinetics satisfy certain conditions, so if they're of activator inhibitor or activator substrate type, and the diffusivity of the activator is asymptotically small, then you have these solutions that are called quote unquote strongly localized. Just to give two quick examples, an activator inhibitor model is something where the reactions are as you would find in, for example, the Gierer-Meinhardt model that Chunyi was discussing earlier. And something like an activator substrate model would be, for example, the Brusselator model. So the key property of these strongly localized solutions that arise in such problems is that the activator is going to be essentially concentrated in a very small region of space. In the case of a one-dimensional problem, the activator concentrates in a discrete collection of intervals, each of which are going to be of order epsilon in length. So the benefit of looking at such a problem is that if you want to talk about equilibrium solutions, you no longer have to deal with the equation itself, but since the activator is concentrating at discrete locations, you can start to talk about where does it concentrate and then what does its profile look like locally. And using that idea, there's a lot of both rigorous and asymptotic theory for proving the existence of such solutions, for asymptotically constructing them, and also for studying their stability. And to give a sense of what such a thing looks like, here's a single spike solution. And you can see that it can start to oscillate. So single spike solutions and actually multi-spike solutions can undergo Hopf bifurcations. Here's an example with two spikes, and you have a different type of behavior where you can have what's known as a competition instability, in which one spike survives and the other one is destroyed. And so we can actually construct the profiles of these 1 and 2 spike solutions and also predict fairly accurately when they will undergo each of these types of behaviors, which makes looking at problems in the singularly perturbed limit kind of a nice breadboard in which you can test different ideas. So I'll be talking about the Gierer-Meinhardt model as well, and we're going to be studying the effects of an inhomogeneous boundary condition. A very brief comment on why we're going to work with the activator, with the Gierer-Meinhardt model, is that when there is homogeneous boundary conditions, there's a really, really large collection of work on the stability, the structure, the dynamics of multiple spike solutions. And so the Gierer-Meinhardt model specifically is a really nice place to test out new types of behavior. So as Chunyi's talk focused on noise, ours is actually going to focus on what happens when you introduce non-homogeneous boundary conditions. So what happens when there is a sudden flux in the activator? We chose to work with the activator because the effects of adding a non-zero flux at the boundaries for the inhibitor, it does cause some changes to the structure and stability of these spike solutions, but it's actually not that drastic of a change. And even though when A and B are equal to 0, so when there is no activator flux, there is a lot of literature, the effects of considering different boundary conditions remain relatively unexplored. So that's not to say that people haven't looked at it. And in 2007, Maney, Wei, and Winter looked at spike solutions in the presence of homogeneous Robin boundary conditions. And there they found the presence of what were called near boundary spikes, and they were able to calculate certain rigorous stability results for that. Another scenario where different boundary conditions have been considered is in the two-dimensional Brusselator model, and this was studied by Justin Zhao and Michael Ward in 2018. And there they considered inhomogeneous Robin boundary conditions on the inhibitor, or I guess for the Brusselator model, we typically call it the substrate. And in both of these studies, they found that are actually fairly substantial changes to the stability and structure of these localized types of solutions. So some other motivation for why specifically we looked at the activator is that by introducing an inhomogeneous Neumann boundary condition, it necessitates that spikes actually form at the boundaries. So when there is no activator flux, typically you find, as Chunyi showed us, is that the spike will concentrate at the center of the interval, and it typically will not move. It can undergo other types of bifurcations, but it'll remain fixed at the center. In the case of other boundary conditions, such as the homogeneous Robin boundary conditions, you could find that these spikes actually concentrate a little closer to the boundary. But when you consider inhomogeneous boundary conditions, so we're going back to this slide, you see that if you have something that's actually 0 at the boundary, there's no way that you're going to be able to satisfy these boundary conditions. And by 0, since these are spikes, I mean that it's 0 and it's flat at the boundary. So the fact that we have these non-zero boundary conditions really necessitate that spikes form at the boundaries. The other technical motivation is that in these bulk membrane coupled models, we often couple bulk bound problems to membrane bound problems using an inhomogeneous boundary condition. The reason for studying just inhomogeneous boundary conditions is that you may be looking at a bulk membrane coupled model and you might see fairly interesting behavior occurring near the boundary. The question is that interesting behavior occurring because of bulk membrane coupling specifically, or is it actually just the fact that there's inhomogeneous boundary conditions at the boundary? So to start the analysis of these localized solutions, first we have to actually construct them. And there are two standard approaches for constructing these. And the one I'm going to talk about is called the gluing method. And the basic idea is to take your unit interval 0 to 1 and subdivide it into a bunch of subintervals. And on each one of those subintervals, construct a spike solution. So what does that look like in practice? You look at solving the same problem on an interval of variable length. And this problem specifically, we can actually solve directly using asymptotic methods. So it gives us a really nice approximation. And we construct just a single boundary spike concentrated at x equals 0. And then what we'll do is we'll fill up the full domain with the solutions obtained on each of these subintervals, possibly with some reflections. And I'll show a picture in the next slide that'll make that a lot clearer. The key takeaway from this construction is that since we are going to be interested in the presence of this activator flux, we have to include a non-zero flux term for the activator. And using the method of matched asymptotic expansions, we find what the local profile looks like. So it's this homoclinic solution for the activator. And this was also made an appearance in Chunye's talk. And this looks just like some kind of hyperbolic secant. And the inhibitor turns out to be some kind of a Green's function. So here it is explicitly. And I'll comment that the psi naught, which gives you the height of these spikes essentially, this is something you can calculate explicitly in terms of A naught and the variable interval length L. The new aspect that arises by considering inhomogeneities is that you have to include what we call a shift parameter. And the shift parameter is chosen so that the boundary condition at x equals 0 is satisfied. So from that boundary condition, you find that it imposes a particular constraint on what y naught can be. And I'll also comment that y naught can also be found explicitly in terms of A naught and L. So once you have solved the problem on an arbitrary subinterval, then the idea is to take each of these subintervals and fill up the unit interval with them. So here we have a 3-spike equilibrium on the bottom of the slide. And you can see we've separated 0 to 1 into 3 intervals, one growing from 0 to this, this variable length LL. Another one, this one here, is going to be of length 2L1. And that's because we've built half of a spike. So this is actually going to be twice of it. And then on the right, there's another subinterval of length LR, so that this point here corresponds to 1 minus LR. Now we want these L values to be chosen so that they actually fill up the unit interval, and that gives us our first constraint on the variable lengths. The second constraint gives us a continuity condition, and this is coming from the fact that the inhibitor is actually non-zero everywhere. So you need to make sure that it aligns at the interface between each subinterval. We don't need to worry about the activator because the homoclinic solution decays exponentially. So far away from here, the activator is actually asymptotically small. It's actually exponentially small. So in a leading order asymptotic theory, these things don't really play a role out here. Okay, so once we've constructed an equilibrium, we're then interested in what is its stability. And this is done by doing a linear stability analysis and linearizing your equations about that multi-spike solution. And I'm gonna completely go over all the details, but using the method of matched asymptotic expansions, you can derive what's known as a non-local eigenvalue problem. So it's a lot like a standard eigenvalue problem, except that we can use the localization of the activator to reduce this big system into a collection of much simpler systems where basically the activator perturbations are concentrating at each spike location, but they are coupled to the behavior of the other spikes through the inhibitor, which doesn't concentrate. And that's actually what results in these non-local eigenvalue problems. And these have been studied quite extensively, both rigorously and using asymptotic methods, in the absence of activator flux. What is the effect of activator flux? Well, when you're looking at the solution centered at the boundary spikes, you have the shift parameter making an appearance. So you have these homoclinics here that are suddenly shifted. And this causes several technical difficulties in the sense that you can't really diagonalize the system in the way that you would when there is no activator flux. And in the case of asymmetric spikes, there's this nice way of relooking at this system as a linear system that's in tridiagonal form. We also can't do that anymore. I'll comment very briefly that the spikes also drift, as we saw in Chunia's talk. And the effect of having these activator flux is that it's an extra forcing term that drives the spikes to the boundaries. And the stability with respect to the dynamics leads to another class of instabilities, and these correspond to order epsilon squared eigenvalues. Basically, these are instabilities that occur over a very long time span. Okay, so we've looked at some of the theory. Now let's look at some examples and try to understand what happens when we introduce the activator flux. So the very first example we're going to consider is what happens when you have an activator flux just at the left-hand side. And we're going to look at the effects that that has on a one spike solution. So a one spike solution can be found just by setting L equals to 1 in our gluing equation. And we can write out what the solution looks like asymptotically directly. Here, YL is the shift parameter, and this is going to be what contains what the activator flux actually does. And there's only one way that this thing can go unstable, and it's through a Hopf instability. And what we find is that by increasing the activator flux, you can actually stabilize that single boundary spike. What do I mean by that? Well, Hopf instabilities are triggered when the time constant in front of the inhibitor exceeds a particular threshold. What we found is that as A increases, this threshold keeps going up. So it gets larger and larger, making it more and more difficult to actually lead to an instability. And the way we calculated this was by first looking at what's known as a shadow limit, which is when the diffusivity of the inhibitor goes to infinity, for which we could calculate that Hopf bifurcation threshold numerically. And then we used that in a continuation to actually study it in the case of finite values of D. So in the middle panel here, we see how the Hopf bifurcation threshold changes with D. And you see that as you increase A, that is, as you move from one curve upwards, that's increasing A, the Hopf bifurcation threshold keeps increasing. And on the rightmost panel, we show what the imaginary part of the unstable eigenvalue goes to. And that gives you a sense of essentially of the frequency that it oscillates. So in a sense, we see that the activator flux has a stabilizing effect. And here we see that as you increase A for a particular value of tau, you can stabilize a spike. So here I'm showing the height of the spike at the left boundary. And you see when A is 0, it starts to oscillate. And then as you increase A, it just is settled. Here is the same scenario for larger values of that time constant. And here I will comment that when A equals 0, in these latter two cases, the spike collapses. But spikes can no longer collapse when you have a boundary flux. They must persist because you have to satisfy that boundary condition. And so this always leads to a case where the spike will start to oscillate indefinitely. The other scenario we considered is when there is a two-sided boundary flux. And in this case, we can't write out the solution explicitly, but the solution is found by solving this algebraic equation for that variable length L. Okay, so for one spike, we have our LL is equal to this little l. For the other spike, the variable length is 1 minus L because it's just a two-spike configuration. And what we found is that you can actually construct symmetric and asymmetric spikes in this case. So a symmetric spike would correspond to L equal 1/2, in which case this equation is going to be satisfied for all values of D and A. So you can always construct a symmetric two-spike solution. However, we found that provided your activator flux is not too large, so it's the same activator flux on both sides and it's not too big, then you can actually construct an asymmetric spike solution. And in some scenarios, that you can construct two asymmetric spike solutions. And what we discovered is that one of those asymmetric spike solutions is always stable. Okay, so if you're in this region in A versus D space, there are two asymmetric spike solutions, of which one happens to be stable. The other thing that we could calculate is the stability of these spikes. And we found that the symmetric two boundary spike solution becomes unstable in the parameter region where only the stable asymmetric two spike solution exists. So what this is saying, I think this next picture gives you a better sense of what's going on, is that a symmetric spike can undergo this competition instability in which classically one of the spikes collapses to zero. However, if the spike collapses to zero, the boundary condition would not be satisfied. So in a sense, introducing this activator flux leads to a stable asymmetric configuration. And I should put maybe quotation marks on stable because it's essentially built into the problem, right? So a symmetric spike in this simulation underwent a competition instability. And instead of having one of the spikes disappear, it went to the stable asymmetric pattern. So this shows us that actually introducing an activator flux introduces a sense of robustness to these asymmetric spike solutions, which classically are always shown to be unstable. Some key takeaways is that by considering inhomogeneities at the boundaries, you will have significant structural changes. You will also have several stability changes. And in a way, it kind of builds in very specific spike patterns. And we encounter these stable asymmetric spike patterns, which go in contrast with the types of spike patterns when Gierer-Meinhardt model. I will comment that there's a recent paper by Kolokholnikov and others which showed that you can also get stable asymmetric patterns when there is a spatial homogeneity, heterogeneity introduced. There's a lot of future directions for that this can be taken. Obviously, considering this in higher dimensions is a good future problem, but also considering spatial heterogeneities around the boundary. So this would be most relevant, I would say, in 2 dimensions or 3. Considering different types of inhomogeneities would be worthwhile. And also using these ideas to kind of figure out with bulk membrane coupled problems, what are the new phenomena that are occurring because of bulk membrane coupling and which ones are occurring just because we start to have inhomogeneous boundary conditions. So thank you for your time.
Thank you very much. This is a very nice talk. Very good work. Again, if anyone has any questions, if you can post them in the Q&A. I'll start out by saying that you've also done some work on bulk membrane coupling. Do you have any kind of, I guess, preliminary insights in how much of the phenomenon in that setting can be explained by thinking of boundary conditions in this way, or how much of it is genuine coupling?
So there's certain aspects of bulk membrane coupling that are very much just bulk membrane coupling. And I think the main one there is a phenomenon of recirculation, where you can have something going on the boundary. It'll go into the bulk and then it'll come back, and this creates these kinds of feedback loops. So in that sense, then it's not just because of an inhomogeneity. However, there are some cases in the literature where people have seen that patterns on a membrane will cause patterns inside of the bulk, but it only occurs on a boundary layer near the boundary. And to me, this kind of study suggests that those types of effects are mainly being caused by inhomogeneities. And I don't know that the bulk membrane coupling is necessary to sustain that kind of patterning behavior. Yeah.
Sure. Okay. Did we have any other questions? So I can question you all day, which I worry about eating up everyone's time. Yes, we have one. Daniel Hull asks, you were saying that these spikes can drift. Does this cause any problems with partitioning of the domain?
Oh, that's a good question. So drift motion is caused by local asymmetries in the spike profile. So usually these things look like hats, but if the hat is a little bit tilted, the spike will move in one particular direction. When you use the gluing method to construct these solutions, if I go back a few slides, let's see. You see that for the interior spikes, which are the only ones that can drift, I constructed them by using a reflection about a certain point. So in that sense, these interior spikes will not drift. There is a different approach to constructing these solutions, which just ask what is the spike location and what is the spike height, essentially. And that type of problem will have more solutions, but some of those will undergo a drift motion. And to give you a very brief sense of where this local asymmetry causing drift comes from, it comes from this term here. Basically, the right-hand side here is the derivative of the inhibitor as you approach it from the left and from the right at a particular spike location. So if there's not symmetry locally there, there's going to be some kind of imbalance. But with the gluing method that we use, you will not have any drift motion.
Okay, well, thank you very much. If there are no other questions, I think we'll move on. But yes, very nice stuff.
All right, thank you.